Welcome back to the Natural Hogarithm. Today we're going to be doing the January 12th hard difficulty daily integral, but most importantly, we're going to be investigating Feynman integration, which is a technique that a lot of complex integrals, like the one you see now, use to turn into something a lot simpler. Let's get into it. Now the first thing we are going to do is introduce a parameter a, and a parameter is just something that we have the ability to change to be whatever we want. Now our integral is going to become a function of a, so instead of being a single finite value, we're going to have a family of integrals. So if we plug in a as 1, we get a unique integral, a equals 2, another unique integral, and so on and so forth. Now our original integral is of course when a is equal to 1 over tangent of 1, then we can see that we just recreate the original problem. Now one of the questions we can ask when looking at this new integral is about the derivative. What is that derivative going to look like? Because we now have a parameter involved. Well, if we do differentiate our integral with respect to a, we can write it as d dA of I of a. And, of course, that is also going to be just equal to I prime of a, I prime being the derivative of I with respect to a. But what does that actually equal? Our derivative is in terms of a, but our integral is in terms of x. So how do we write this out? Well, the answer to taking that derivative with respect to our parameter is differentiation under the integral sign. This is the trick that Feynman integration uses, so let's go into it and let's really make sure it makes intuitive sense before we actually apply it to our problem. Now, here is an example function, e to the negative x. I've sketched it out, and I've also drawn, using a Riemann sum approximation, what that integral of e to the negative x would look like. Now, one question that we have to ask is, what if we introduce a parameter? Let's introduce that same parameter a into our problem. Here's what the new function looks like with our parameter. Again, f is now a function of our parameter a and of x. And drawn in orange, we can see that it now sweeps out a new area too. We've accumulated these blue rectangles. Now, the total area underneath this curve, I'm going to rewrite as a new integral, I of a. I'm going to rewrite it in blue just because we've accumulated that blue area. And again, it's simply going to be the integral from 0 to t of our new multivariable function with respect to x. Again, we're chasing how this area actually changes with respect to our parameter, and we can see that when we introduced our parameter, our area a changed by some amount delta a, which from the graph is simply the sum of all of these blue rectangles. Now, every individual rectangle's area is just the length times the width. But what are these dimensions? Well, the width of each of these rectangles is just going to be the change in input between each rectangle, which is defined to be delta x in the diagram above. And the height is going to be the change in output of the function. Now, that change in output is going to be the trickier part to define, but I'm going to go ahead and define it now and then explain what each part actually means. So that change in output is going to be the partial derivative of f with respect to a multiplied by a tiny change in a. So the first term there, that partial derivative of f with respect to a, is simply describing how f changes as a changes. And then that second component, that dA, is simply the change in a. Now, if you put all of that together, the first term tells you how f changes with a, and if you apply a change in a, well then you just recreate how f actually changed. Now that change in area is the sum of all of the areas of each rectangle, and the area of each rectangle from the dimensions below is length times width. Our length is the partial derivative of f with respect to a times dA, and our width is delta x. So there we go, length times width, add them all up, and we're good to go. With this new form for delta a, I want to take the limit as delta x, which is the rectangle's width, goes to 0. This is going to do two things. Not only is it going to make our delta a, our approximation for change in area, more accurate, but it's also going to turn all of our terms into differentials, which is what we need to take a true derivative. Now this delta a is going to go to, again, this differential dA, this infinitesimal change in area. And if we work over on our right-hand side now, the sum in the limit is going to go from a discrete sum to a continuous sum of differential components, which is an integral. We can see that up above. These discrete rectangles are going to get thinner and thinner, smaller and smaller, as delta x goes to 0. And so we're going to be adding up differential components of area. That is, by definition, what an integral is doing. It's adding up continuously a bunch of differential components of area. Now, the partial derivative of f with respect to a is not going to change as delta x goes to 0. However, our delta x at the end is of course going to change. If it's approaching 0, we can just say that it's going to equal some infinitesimally small change in x, a dx. And that is it. That is our differential representation of a change in area as we change our parameter. Now the final thing I'm going to do is divide both sides by dA. dA is independent of x, so I can bring it out of our integral, and the left-hand side now, our rate of change of area with respect to a, is exactly what we've been chasing this whole time. That is I prime of a. And that's simply going to be equal to the integral of the partial derivative of f with respect to a dx. And that's it. That is what we were after. What this result tells us is that if we have an integral as a function of a parameter, if we wanted to differentiate with respect to that parameter, we could differentiate under the integral. In other words, bring that derivative inside and apply it to our integrand. Now, this idea of leveraging a parameter extends far beyond simply using e to the negative x. We just went through a general proof with a general function. This idea of differentiating under the integral is what makes Feynman's technique so powerful. We can differentiate a parameterized integrand and produce a whole new integrand, giving us more mobility to tackle complex integrals. Without further ado, let's return to today's integral and apply this idea to try to flesh out a solution. Now that I've rewritten our integral on the next page, let's apply Feynman's technique to this problem. So if we wanted to differentiate I of a with respect to a, we could get that I prime of a is simply equal to the partial derivative of our integrand with respect to a. And now all we have to do is work through what that derivative might be equal to and see if it simplifies. To evaluate our partial derivative, we need to realize that sine of x and x are both independent of a, meaning that when we do go to take our partial derivative, these can be treated as constant, so we can actually bring them out front. Now the remainder of our derivative is simply the derivative of e to the negative ax with respect to a. That means that we can treat x as constant, and when we do go ahead and run this derivative, we're just going to be left with negative x e to the negative ax. Now what should immediately jump out is that these x's do cancel, and our integrand is simply a trig function and an exponential left over. Now for the remainder of the problem, we're going to apply integration by parts. Integration by parts is a very useful integrating technique. It sort of undoes the product rule, and for those of you who aren't aware, it follows the form that the integral of u times dv is equal to uv minus the integral of v du, where u and v are both functions of some variable. In this case it would be x. I'm going to let u be e to the negative ax, and I'm going to let dv be equal to sine of x dx. And now we're ready to integrate. Now I'm not going to go into too much depth about the actual procedure of integration by parts, but my work is playing out behind me right now. This is our uv term evaluated across our bounds, and this is our v du term. And once everything is said and done with all of our differentiation, we are left with this expression here. And we're going to go ahead and distribute this negative to both of our terms just to clean things up a bit. And now we're left with two terms, our uv term on the left and this integral on the right, which we're actually going to apply integration by parts to one last time. Now, before we go ahead and do that, I want to work with the term on the left, which is this uv term evaluated across our bounds. Now, the first thing I want to notice is that e to the negative ax can be rewritten as 1 over e to the ax, because that negative exponent brings it into the denominator, and so the term that we're evaluating across our bounds is actually equal to cosine of x over e to the negative ax. Now, even if our top bound is infinity, and it's not mathematically rigorous to just plug in infinity, I'm going to do this for the sake of conceptual understanding. Our top bound is going to be cosine of infinity over e to the infinity, and our bottom bound is cosine of 0 over e to the 0. Now, this top bound is interesting. Cosine of infinity does not have a defined value, neither does e to the infinity, but cosine itself as a function is restricted to the range of -1 to 1, right? for every input in our cosine function, it's going to spit out something between -1 and 1. Whereas e to the infinity, and any exponential for that matter, grows boundlessly. As our input approaches infinity, e to the infinity also tends to infinity. Now, if we're dividing something that's finite, something that's between -1 and 1, by larger and larger and larger values, this whole term is going to go to 0. Our second term is cosine of 0, which is 1, over e to the 0, which is also 1. 1 divided by 1 is 1, and since our top bound evaluated to 0, this entire term is simply equal to 0 minus 1, which is equal to -1. Plugging this back in, we get that I prime of a is equal to -1 plus a times our new integral, which is of cosine of x times e to the -ax dx. Like I said, we're going to do integration by parts one more time on this integral, and a very handy substitution is going to be made possible. I'm going to again let u equal e to the -ax, and dv equal our trig function, which is cosine x. I prime of a is therefore -1 plus a times our integral. If we expand using integration by parts, we're going to get the following form. Again, I'm not going to explain my work, but this first term is our uv term evaluated across our bounds, and the second term is our new integral evaluated across our bounds. Now I'm once again going to evaluate this uv term across our bounds. Now, it looks very similar to our previous term, and in fact I'm going to use the same idea of e to the -ax being a negative exponent, so I can bring that to our denominator. We're going to be left with sine of x over e to the ax, evaluated across our bounds. And again, I'm going to do the same sort of not rigorous but conceptual plug-in of infinity. We're going to get sine of infinity over infinity minus sine of 0 over e to the 0. Now once again, our trig function sine here oscillates between -1 and 1. Its range is confined between that space. Now e to the infinity, of course, and e to the x in general, is going to grow boundlessly, and so this term is again going to go to 0. Now our second term is sine of 0 over e to the 0, which is simply 0. Now 0 minus 0, should be able to do that in your head, that is 0. And so this entire term is simply 0. Now we can rewrite I prime of a, plugging back in that term that's equal to 0. We get -1 plus a times the quantity 0 plus a times our new integral. We can then distribute this a to both of our terms. A times 0 is of course 0, and a times a is a squared. All we're going to be left with now is -1 plus a squared times our integral. Now, if we clean up this excess parenthesis here, we can see that I prime of a fits this form, and this integral should look familiar. In fact, it's actually equal to -I prime of a. We can see why this is true from where we first did integration by parts. This was what I prime of a was equal to initially. With the slight exception of this negative sign, it is exactly what we have currently, and that's why we can go ahead and plug it back in. Plugging this in, we get that I prime of a is equal to -1 minus a squared I prime of a. Now, all we have to do is solve for what I prime of a is equal to. This is just some basic algebra, and I'm going to play out the steps on screen now, but with some slight factoring and some dividing, we can solve for what I prime of a is equal to in terms of a. And now all we have to do to get back to I of a is simply integrate. Now, writing out our integral, we get that I of a is equal to the integral of -1 over 1 plus a squared dA. Now, this form fits a very well-known integral. In fact, this integral expression is simply equal to negative arctangent of a, and then we have to add that constant of integration because this is an indefinite integral. Perfect, now we have two expressions for I of a. We have our original expression here, and we also have our new Feynman expression down here, which is only in terms of our parameter. Now let's recall what we're actually interested in, right? Our original integral was I evaluated at 1 over tangent of 1. That is the value that we're actually after. And we're not going to plug it into our first expression, but if we plug in 1 over tangent of 1 to our second expression, well, we can see that I of 1 over tangent of 1, which is, again, what we're looking for, is equal to negative arctangent of 1 over tangent of 1, but then we still end up having, on the tail end of this expression, our plus c. If we can determine what our constant of integration is equal to, we can evaluate I of 1 over tangent of 1 and get our answer. Now what I want to look at is the behavior of both of our expressions as a tends to positive infinity. As a approaches infinity in our original expression, e to the negative ax approaches e to the negative infinity. E to the negative infinity approaches 0 for larger and larger a, and therefore this entire integral actually goes to 0 as a approaches infinity. As for our second expression, as a approaches infinity, I of a approaches negative arctangent of infinity plus c. Because both versions of I of a are equivalent, we can set these two forms equal to each other, so 0 is equal to negative arctangent of infinity plus c. We can solve for c, therefore, by adding arctangent of infinity to both sides, and arctangent of infinity asks where tangent is equal to infinity, and that's simply at pi over 2. So c is equal to pi over 2. We can plug this back into our expression for I, which again is equal to I evaluated at 1 over tangent of 1, and that was simply equal to negative arctangent of 1 over tangent of 1, plus our constant of integration, which we just solved to be pi over 2. Let's simplify this. Now I'm going to introduce the following arctangent identity. It states that arctangent of some input plus arctangent of the reciprocal of that input is simply equal to pi over 2. Now let's prove where this comes from before we apply it to solve for arctangent of 1 over tangent of 1. Let's imagine a right triangle with side lengths of A, B, and C, about as general as you can get, and then we'll label this angle theta, and this is 90 minus theta, but in radians that would be pi over 2 minus theta. From our triangle, we can define tangent of theta to be A over B, and we can also label tangent of pi over 2 minus theta to be B over A. Now we can also define our angles, so theta itself is going to be the arctangent of A over B, and pi over 2 minus theta is going to be the arctangent of B over A. What we can do now is add these two expressions together, and when we do that we can see that the thetas are going to cancel, right? We have a positive theta and a negative theta, and so all we're going to be left with is pi over 2, and that's going to be equal to arctangent of A over B plus arctangent of B over A. Now if the identity hasn't already jumped out at you, let's let A over B equal x. So we can replace this A over B with an x, and we can replace B over A as the reciprocal of A over B, which is just 1 over x. And there we go, that is where our identity comes from. Now that we've proven our identity to be true, why don't we go ahead and use it? So we'll let x be equal to 1 over tangent of 1, and when we do go ahead and apply our identity to this form, we're going to get this expression here. From here we can isolate arctangent of 1 over tangent of 1. Again, that's what we're trying to solve for, so we can plug that back into our integral expression. But we can simply see that that's equal to pi over 2 minus arctangent of tangent of 1. Now, arctangent and tangent are inverse operations, and so we're simply going to be left with 1. Alright, now that we have this value for arctangent of 1 over tangent of 1 found, we can plug this back into our integral expression and simplify a few things and we will be done. Now again, we have to keep that negative sign out because the arctangent was negative. We can plug in our pi over 2 minus 1, add our pi over 2 on, and immediately we can see that some things cancel. Those negative pi over 2 and positive pi over 2's cancel each other out, and negative 1 simply leaves us with 1. After all of this work, after our parameter, after our differentiation, after integrating back, after taking limits to find what our constant of integration was, our integral simply spits out 1. Thank you so much for watching. I really hope you learned something new today about differentiation under the integral sign, or Feynman's technique. It's a really powerful method to condense complex problems like this one and many others like it into clean results. Without further ado, I've been the Natural Hogarithm, and keep integrating.